it's a crazy scenario, but this number is so big that just imagining its decimal expansion but you can never even get close to it. Your head would collapse into a black hole long before you got near it.
Hello, this is Robinson Earhart here with Pins the Podcat and the introduction to Robinson's podcast, number 155. And this episode is with Tony Padilla, who is professor of physics in the School of Physics and Astronomy at the University of Nottingham, where he's also the associate director of the new Nottingham Centre of Gravity, where you won't be surprised to hear Tony works in cosmology, quantum gravity, and related areas. He's also a host of the YouTube channel Numberphile and author of the book with the phenomenal title, Fantastic Numbers and Where to Find Them, A Cosmic Quest from Zero to Infinity. And in this episode, Tony and I discuss some of these fantastic numbers. We start off, if memory serves correctly, with two related philosophical questions, that of mathematical Platonism, so whether mathematical objects like numbers or sets or anything else might have a mind and physical world independent existence in some other realm, what is usually thought of as or called the Platonic realm or the set theoretic universe if you're talking about sets. And then we talk, I think, about indispensability, which is the question of whether mathematical objects are necessary for physics, or that's one way of putting the issue. Then we move on to just a few of these wild numbers that are discussed in Tony's book and how they relate to our world. The first issue we discuss is just how big the universe would have to be to contain doppelgängers for all of us, and how far we might have to travel to find one. And then we get into two particularly large numbers, very large, very, very, very large numbers, Graham's number and Tree 3, which you might have heard of the first one. I doubt you've heard of the second one, but maybe you have. So there are links to fantastic numbers and where to find them, and Numberphile, the YouTube channel, both in the description. And please leave likes, comments, subscribes, all of those things. So helpful. I cannot underscore this enough. So without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Tony. In the dedication to fantastic numbers and where to find them, you write that your daughters call you Gilderoy, and my detective skills tell me that based on this and the title, you and your family are Harry Potter nerds.
Well, I think that's probably fair. They're more. I mean, I've read them all, but yeah, they're more so than me. And yeah, so basically, the way that comes from is that anytime I mentioned anything about the book, I was getting like, they just go Gilderoy, because of course, Gilderoy Lockhart famously in Harry Potter writes these books and sort of shows off about it all the time. So I guess that's their way of keeping my feet on the ground. But that's
I see.
Yeah, they're all upset.
He also has a very big smile, and you have a very nice smile too.
Oh, well, that's nice to say. I don't know about that, but
thought that might have been it. But okay. Good. Granted that you're a physicist, though, and not that has anything to do with Harry Potter, and physics is full of numbers, large and small, and also delicate. Last night, I just spoke with Draint Lewis about fine-tuning, so that's on my mind, the delicateness of these numbers. How was it that you came to write a bestiary of numbers?
Yeah, well, I mean, so even though I am a physicist, like a theoretical physicist, I came to it through maths. I mean, my background is one in maths. I did my degree in maths. I did my PhD in a maths department, even though it was kind of a theoretical physics PhD. So that's always been my background, and I've always had this fascination with numbers. I tell a story in the book about how when my mum and dad got me this dictionary for Christmas, and so one first thing I did with it was like, okay, dictionary, okay, this is words, right? But, so I had two interests, and one of them was football and soccer, as you guys call it, and the other one was numbers. So I was like, what am I doing with this? How's this going to help me with these two things? So I decided I was going to use this dictionary to look up numbers, and I sort of went through it, and a million, and then a billion, and then a trillion, and I sort of spotted the pattern. I saw there's something going on here, right? So I ended up finding a centillion, which was a 1 with 600 zeros in the old British system, and then from there, and that's kind of, so it was just sort of devastating. And it kind of, I didn't get any more numbers, I didn't get any higher than that. I love the idea of this massive number, which was way bigger than anything you'd seen before. But of course, I didn't know about a Google or a Googleplex at that time. And or even Graham's number, right? So I've always had this love of numbers, and I think as I sort of developed, I think I really enjoyed how numbers sort of fit together with physics. I think that's, for me, I've always thought about how do you bring numbers to life? Like, so you can, there's two ways of being a mathematician in some sense, right? You can be a real pedant, a real hardcore pure mathematician, or you can be someone like me, who I would say is a little bit more relaxed, perhaps, and wants to bring numbers to life in another way, and bring them to life with, give them personality using physics, seeing how they fit into the physical world. And that's really sort of, where I came from. And so as I developed as a mathematician, I started to branch more and more into theoretical physics, and that was the area that attracted me the most. And but I never lost that love of numbers. And then when I started making the YouTube videos, one of the things that we did was try to put those numbers into physics, into the physical world. And when you're talking about a number like Graham's number or Googleplex, these are massive numbers. It's quite hard to fit them into the physical world in some coherent way. So you're naturally led to sort of really, really extreme physics. And so that's kind of the spirit of what I was trying to do with the book. It's just a sort of fun. It's like a ride of physics and numbers, and in the most extreme environments for both.
Mm-hmm. Yeah. Speaking of your love for soccer/football, before we started recording, you already compared Witten and Maldacena to Ronaldo and Messi. So it's front and center. But
which one's
a good, yeah, a good place to begin is where you just said how numbers and physics come together. And I figured that before we get into specifics, we should deal with this a bit more generally. And as a physicist, though, this isn't the rule, of course. I'm just going to assume, though, correct me if I'm wrong, that you believe in the reality of unobservables like electrons or quarks that are vital to our most successful theories, even if they might boil down to something else like strings. But how do you conceive of some of the numbers that go along with them? Are you someone who believes that they too have an objective existence of some sort, or maybe that they're just part of a language we use to describe and compare what we observe? And I imagine that having this mathematical background and the physics expertise as well gives you an interesting perspective on the matter.
Yeah, I mean, so it's nice that you talked about electrons, actually, in that context, because as soon as you do that, you know that you're going to need, when you write down our theory of electrons, it involves imaginary numbers, right? So you write down a theory, you need to use imaginary numbers to actually, write down the theory. And so, of course, but what is an imaginary number in any sense part of our physical world? Does that really make sense? We certainly don't measure imaginary numbers in any sense, but the thing we use to describe that theory of electrons does use them. So, I mean, I think it's a very deep question, and it's one really for the philosophers, and there are many different ways you can think about it. You can think about sort of, whether numbers, they're obviously a man-made construction, but are they really part of the physical world, or are they separate from the physical world and just a tool for describing it? And one of the things I always think is fascinating when you think about this is the way, and this goes back to Wigner's famous essay in the 1960s, where he talked about the unreasonable effectiveness of mathematics. And so we have this universe, right, with all the wonderful things that happen in it, expansion of the universe, neutron stars collapsing into black holes, wonderful, amazing physics, the microscopic physics that we can talk about, whether we're talking about particle physics or string theory or whatever, but whatever we use to describe, but ultimately there's stuff going on, right? And we're using mathematics to describe it. And mathematics does an incredible job of doing it, right? But we've got absolutely no right to expect it to do that, because ultimately maths is a man-made construction, right? So, and yet it does this incredible job of describing the universe. Will it continue to do this incredible job of describing the universe as we probe more and more deeply into the into the micro world? I don't know, but it's incredible that it has done. We've come up with this tool, this thing which we call maths, and yet it's just done this fantastic, and with all its wonderful things like imaginary numbers and irrational numbers and all these things that really, really hard to intuit in some sense. And yet they describe the world, it enables us to describe the world so wonderfully well. And I think that is fascinating. How long we can ride that for, I don't know. One of the sort of great mysteries, it's to be very philosophical, is in the nature, what is quantum gravity? I would be a proponent of string theory, but maybe part of that question is understanding the true nature of infinity and what is infinity, and of course that touches on mathematics as well, and how to understand infinity in mathematics. So is nature going to play ball there too? We don't know. It's still that one of the great final frontiers of theoretical physics is what is the nature of quantum gravity and all the infinities that arise there. How do we control them? So yeah. The relationship between numbers and physics is one that's served us really well, but I don't know how long we can continue to rely upon it. Who knows?
Well, just for me to clarify what you were saying, you used the word tool a number of times in describing mathematics. Can I take that as meaning that you don't epitomize the view of a Platonist per se, where we are inventing math, we're not really discovering it? Or maybe you think we are discovering it, we're making discoveries about a universe of sets, but our description, the mathematical logic, the way we describe it, is still a man-made construction.
Yeah, I would say my view is that it's man-made. I'm open-minded on this, and I've seen things that people like Max Tegmark have sort of speculated on this about the mathematical universe. The idea that all things that are mathematical are kind of realized, and they are part of this sort of greater multiverse. I think within mathematics itself, it's not always clear that that's consistent. And, we know from, going deep into sort of Gödel's ideas about incompleteness that sometimes, it's not clear that mathematics itself is always going to be self-consistent, arbitrarily. So I think for that reason, I'm inclined to think of maths as a tool and a man-made construction, which is really good for describing our universe. But can we do that forever? I'm not convinced. So it's a really interesting point, actually, because I guess this is where the physicist comes in, right? This is where, so one of the things that you can think about is, how do we define our theories in physics? How do we build our theories? Well, on some level, we have two things that we can use. On the one hand, we have, mathematics, and there's the consistency of the mathematical model, and that it makes sense, and that there's no internal inconsistencies that the mathematics can show. That's really important and a really powerful tool. It's really good. But the other tool that we have is, of course, experiments. And at the end of the day, experiment always wins. It will always win. And it's as somebody with a math background, it's sometimes hard to remind yourself of that, but it's ultimately true. Experiments is always the winner, because you go with what you see. Now, of course, that doesn't mean that you shouldn't question the experiment sometimes, and that's happened in the past, and where experiment doesn't seem to really make sense. And then, of course, there's found to be issues with the experiment themselves. But that's to say that ultimately experiment is ultimate arbitrator, and we must always remember that. But that doesn't mean at the same time that we can't use maths as a way to guide us, because I think we can, and we do, and we have, and that's one of the themes of the book, actually.
Yes, you mentioned Max Tegmark a few minutes ago, and that's actually where I wanted to start our journey into this bestiary of numbers. But before that, I an episode came out yesterday with Andy Strominger on string theory, and I just wanted to go back to something you said even earlier, which is so that understanding infinity is particularly important for string theory. And I was wondering why it comes up there rather than with just quantum theory or just general relativity. Why is infinity so particularly important for string theory?
Well, I wouldn't necessarily mean for string theory. I meant the problem of quantum gravity. So the reason is that so we have this when we try to sort of study the quantum corrections to so let's take the electromagnetism, quantum electrodynamics. When we consider the sort of quantum corrections to the theory of an electron and a photon, we actually find infinities that appear. Okay, so this is Oppenheimer. Oppenheimer. So it was very topical at the moment. It was Oppenheimer who was working on a calculation, sort of suggested to him by Pauli, where he was trying to calculate the spectral lines of hydrogen, and the quantum corrections to that in this new quantum theories quantum field theories that we were using. And what he showed was that there is the answer he's getting infinite answers, and so these infinities are appearing even in quantum electrodynamics. But what you find is there's a way to handle them, and it's a process which we call renormalization, where essentially, and this is a bit of a loose way to say it, but essentially what you do is you take that infinity and you kind of sweep it under the rug, as Feynman put it, right? You literally cancel it off with another infinity. It's the kind of thing that turns mathematicians' blood cold, right? But it kind of works. And when you do this in a consistent way, what you find is that ultimately, in the case of QED, you just have to do this for the mass of the electron and the charge of the electron, and then all other observables that are related to them now fall into place, and you can make concrete predictions and come up with a predictive theory. And there are only two quantities that you had to sort of do a sleight of hand with, and it all works beautifully. And so that allows you to sort of make experimental predictions, because you do your sleight of hand twice, once for the mass, once for the charge, and then all these other experimental predictions fall into place, and you can test them. Now, the problem is when you try to do this with gravity, so in other words, when you're trying to do quantum gravity, there isn't just two things that you have to sort of do this sleight of hand with. Actually, there are an infinite number of things. So what happens is in quantum gravity, there are an infinite number of infinities. Okay, so there's an infinite number of times you have to do this sweeping under the carpet, this sleight of hand that worked really so well with QED. And so that's not a predictive theory. That's just not something you can work with. And so this is what I meant by saying you've got to try and control the infinity. So what happens with quantum gravity is that just infinity after infinity after infinity just comes popping out of the quantum correction to the theory. And it just gets worse and worse and worse. So the one thing you can do is you can cut the theory off. You can say, I'm not going to trust the theory beyond some very high energy scale. Typically, you take that to be the Planck scale. And just say, if I don't even try to go any higher than that, and that kind of resolves the infinity, but it also restricts the regime of applicability of your theory. And in the case of, if you're veering near a black hole singularity, your theory is going to break down, right? So you want to be able to do quantum gravity. You want to be able to push the theory up to arbitrary high energies, just as you were able to do with QED. And well, unfortunately, at this stage, that naively requires you to have this infinite number of infinities. String theory, on the other hand, is kind of gets around these problems by giving extent, introducing a natural scale, which is the string scale, which kind of sort of smooths everything out in a really elegant way. But that's what I meant by sort of the problem of quantum gravity is perhaps in some sense related to the problem of infinities and understanding the nature of infinity, or not. I mean, we don't know.
Well, thanks. That was really helpful. And we could, of course, talk about string theory for days on end. But I think we'll still be talking about infinity when we turn now to Max Tegmark and Doppelgängers. And I believe I recall in reading Fantastic Numbers that he introduced this question of our doppelgangers in the universe and how far away they are. I don't know if you think it would be best to start with Max's formulation of the problem, because I know you treat it a little bit differently. But maybe first we could start with just what a doppelganger is supposed to be.
Well, even that question is not a clear
yes.
one, right? Right. So very naive. Okay, so traditionally a doppelganger is something that looks exactly like you, right? And in the book I tell the story of my mum's cousin Gerard, who claimed his dad had seen his doppelganger. In Irish legend, that meant that you were going to die, and then he died a week later. So this was many years ago. But so anyway, the I guess in some sense you can say, well, what is a doppelganger? Is it somebody who just looks like you, or is it somebody who actually is exactly you? What do we mean by exactly you? Do we mean that it's in exactly the same quantum state, or do we mean that it's some sort of, because you're a macroscopic object, are we thinking about some sort of, do we really care about whether the electrons in between, are spinning up or down in your sort of small intestine? Do they have to match with your doppelganger? Is that do we need that level of accuracy? Or are we happy to average over some of that discrepancy? And so, in some sense, you could think about an exact copy, literally an exact copy where it's literally in the same quantum state. But you can never really sort of probe that, because you've got to try and identify what state you're in, right? And if I'm going to take you, Robinson, and trying to figure out what's your exact quantum state, I'm sorry, but I'm going to have to vaporize you, right? Because I've literally got to sort of figure out what the state of every single degree of freedom that makes you up is in. I'm going to vaporize you, destroy you anyway, so it's not ideal. But anyways, so very loosely, we're talking about an exact copy to some approximation, and you can sort of speculate how accurately you want that to be, and you can make it really accurate in principle.
Yeah, so maybe a good way to start is with this just naive formulation of the problem. And as I understand it, it is, if the universe is extraordinarily large, far larger than the observable universe, which it presumably is, then certain configurations of matter will recur. And naively, my doppelganger, without getting into what actually constitutes a doppelganger, just something that is me, will be found as we look farther and farther away from Earth, because these configurations will recur just because of the immense amount of mass in the universe. And the question is, how far away do we have to look before we will find my doppelganger? Would you say that that's a reasonable way of putting the problem?
I wouldn't talk about mass, but with that caveat, yes, I think that's fair enough. Yeah, I think it's really the question of, so you look at the sort of volume of space that you occupy, right? And you ask the question, how many different ways can I arrange a volume of space that size, right? What is you're one arrangement, right? I'm another arrangement, right? A cow is another arrangement. Empty space is another arrangement. There's lots of different possible arrangements that are, let's say, roughly a cubic meter of space could be in. And so the question is, how many arrangements are there? And of course, as the universe gets, and then you can sort of imagine yourself. So it's some number, some very big number. There's lots of possible. Is it infinite though? That's the real question. Is there an infinite possible ways in which you can arrange a cubic meter of space? And so that's the key question. The answer to that is it's not infinite. And there's a reason why it's not infinite. There's two reasons actually why it's not infinite. One is quantum mechanics, and the other one is gravity. Those two ingredients guarantee that number is not infinite. Quantum mechanics kind of discretizes things all over space, and it gives you a sort of a building block. That gives you almost straight away a finite piece. And also gravity itself, that's space-time. And so when we talk about quantum gravity, we can think about breaking up space-time in a finite way. So straight away, we've got this arrangement of a cubic meter of space. We can go into that into more detail. And the number of ways in which you can arrange it are finite. It's a finite but very large number. Now, but if the universe is big enough, you can imagine sort of, I start off with you, Robinson, one arrangement. of that cubic meter of space. I then go alongside you and I sample the next arrangement and it's different. Okay, so I've now sampled 2 and I keep moving across this gigantic universe and I keep sampling these cubic meters of space. Now, eventually I'm going to move through so many possibilities that I will start to see repetitions. Now, you might say, well, okay, fine, but you're going to see the more likely repetitions first. Of course, that's obviously true. Not everything is equally likely. I mean, I would absolutely, for example, empty space is going to be far more likely than a Robinson, right? Clearly true. But the Robinson is clearly not vanishingly unlikely, okay? And actually, if you go to sufficiently large universes, then even the unlikely things will start to repeat. It's just like, it's just inevitable. And this is one of the ways in which I try to sort of imagine a Googleplex and how big a Googleplex really is. That if you imagine a universe that's a Googleplex meters across, then actually the chance that you would have to be almost essentially vanishingly unlikely not to have a doppelganger somewhere in a Googleplex universe, which is remarkable, right?
It is. Let's, if it's okay with you, let's get into the arrangements of space in more detail. And why does entropy figure into how you think about this question? And first, I might ask you to explain just how you think about entropy, since you write that most people introduce it as analogous to a measure of disorder, but that this is it's imprecise. Maybe it's not the right way of looking at it.
Yeah, I mean, that's the standard story, right? And I know it's not a terrible way to describe it. It's fine for its purpose. But so for example, just to flow with that a second, people will talk about a bedroom. A tidy bedroom has a low entropy, and a messy room has a higher entropy because it's more disordered. Well, actually, do you know what? That's true in a way, but let's try to unpick that a little bit to try to better understand what entropy really is. So let's suppose you have a tidy room, right? And you've got a bed arranged really nicely. There's a teddy bear sat on the bed. There's an alarm clock next to the bed. There's a book there maybe. Okay, now you run into the room and you look at it. And you've got 2 seconds to just absorb the information and figure out what's in the room. Okay, and where it is. Now, because the room's nice and tidy, and then somebody shows you a picture of another room, and you've got to say, is that the same room? You probably got to do a pretty good job of getting that right? Because you knew the teddy was there. You saw the teddy. You saw the alarm clock. You saw the book. And it was all organized, and you were able to sort of distinguish this room from another room that is different, right? That has perhaps the teddy in a different place, or the alarm clock showing a different time, or a different book, So you can tell the difference, okay? But suppose you do something. Suppose that room is not a tidy room. Suppose it's a messy room. Stuff strewn everywhere. Teddy's there, but it's under a pile of clothes. It's a little bit of it sticking out. Alarm clock's just, got glasses in front of it. The whole thing's chaotic, right? And now you do the same trick and you run into the room and you do your 2 second, sort of recording what you see. And then somebody shows you another room, which is similarly messy. And you've got to figure out, is it the same room? But maybe the only thing different is the teddy was moved to a slightly different place. But because it's such a mess, you can't tell. It just looks like the same room. That's really, so that's why it has a higher entropy. So what I'm really getting at here is entropy is really the number of different ways in which you can sort of kind of average something, in which you can get something to look the same. Okay? So let me give you another example. So an egg, take an egg, literally an egg. So you can ask, well, this has got entropy. Now why? Why has it got entropy? Because I look at the egg, right, and I see it's an egg. It's a certain size, it's a certain weight, a certain temperature, it looks a certain way, right? Now there's loads of missing information that I don't see. The specific arrangement of all the atoms within the egg, all that detail. Now that's detail I'm sort of washing away. It's like the detail of the messy room, of how the clothes were strewn everywhere. It's that detail. You don't worry about that detail. You kind of average it out. Your brain sort of just washes it away. And so when you're looking at the egg, you're not worrying about all the arrangements of all the different atoms. Now you might have another, so to describe that egg and describe it, the level of approximation you're willing to do, there might be lots of equivalent things that essentially, as far as you're concerned, are exactly the same egg, because you don't care about the arrangements of the atoms. You're not measuring that. You're measuring these macroscopic quantities, and there might be lots and lots and lots of different microscopic arrangements that yield the same macroscopic egg, right? And so entropy is really counting all those different possible microscopic arrangements. That's what it is. We call them microstates. It's counting all the different possibilities that give the same macroscopic output. So in the case of an egg, it's just like, it's all those different possible ways you could have arranged the atoms. They still get the same egg as far as you're concerned. In the case of the bedroom, it's all the different possible messy arrangements of the clothes and all that you don't sort of disentangle. Now, that's what it is. It's all those different microscopic ingredients. So entropy, in some sense, is a measure of missing information. It's a measure of the number of ways, the hidden ways in which you can arrange something. And so that's why it's important for counting the number of ways in which I can arrange a cubic meter of space.
This, though, I'm not sure is going to connect necessarily with our question of doppelgangers, but another conception of entropy that you introduce is that, unless I'm mixing books up, I don't think I am, but it's that of a jailer holding back energy. And how does this picture connect with the microstate, macrostate idea?
Yeah, so it's yeah. So I think I give sort of an analogy in my book about somebody breaking into a house, and so this goes back to the original idea of entropy and the sort of idea of change in a system. And the transfer of heat in particular. You're thinking about how heat transfers from one place to another, and what's really the agent of that change? What is entropy? It's the growth of the number of states in the system. So you can think about entropy as the agent of heat transfer, and that's how it was originally formulated back in the day, in the Victorian times, by those early physicists. And of course, it was Boltzmann that came along and then understood that this was actually the growth of the number of states of the system. But one of the things that we know is that if you have a system of heat transfer, that as you eliminate the sort of gradient in the heat gradient in temperature, then you shut down heat transfer. There's nothing else to do. Right. And so the growth of entropy is related to this desire to sort of shut down the amount of available work there is in the universe. So it's trying to shut down all these gradients. So, you can try to generate, move energy from one place to another. But what the growth of entropy does is it tries to shut that down. It tries to slow that process down. So the way you can think of it as somebody breaking into a house. And this burglar is trying to sort of take out, trying to go through the house and sort of take out all the, as much of the jewels as they like. But ultimately, as everything just grows, the number of room grows, it just becomes harder process for him to drag this stuff out. I don't know if that's a perfect analogy, but that's it. What Boltzmann realized was this change of the system was related to this shutting down of work, of available energy, was related to the growth of the microstates of the system. That it's just there's fewer places. You're using up all the possibilities in some sense.
Okay, no, great. That connects it too. No, it's very helpful. And before we turn to the Googleplexian metric of size of the universe, I'd like to still better understand the composition or configuration of our doppelgangers. So you already alluded to this, but how does quantum indeterminacy affect whether there can be a true doppelganger to you or me, or if we're even determinate things to begin with? I guess I'm wondering what the final number is you arrive at for how many different possible configurations there are of a volume of my size or something like that.
Yeah. So I mean, again, this kind of relates to how much information we want to wash away and not worry about. Do we average over the state of electrons in your small intestine? Is that something we want to wash away, or not? Right. Actually, so when I do the estimate in the book, I end up not washing those things away. I literally think of you as a pure quantum state. Now, it's a strange thing to do because in some sense, you are in some sense a pure quantum state, but nobody's ever going to really think of you like that because I never measure all your degrees of freedom. I don't measure those electrons in your small intestine. I don't do it. I don't know them. I'm averaging over them. Any measurements I do of you is averaging over those possibilities. And so I don't really think of you as a pure quantum state. I think of you as actually really as a mixed quantum state, where I wash away those possibilities and I average over them. But in truth, I can think of you as a pure quantum state, and in some sense, you are one. And so if I do that, I can ask how many pure quantum states can there possibly be in a cubic meter of space? And I can do that calculation based on my understanding of gravity and the counting of degrees of freedom, the counting of those ingredients. And maybe that's something we can go into now, but that's how I do it.
Okay. And do you recall roughly what the number you come up with is?
Oh, I think it's 10 to the 10 to the 69, something like that.
Okay.
It's something
so
like
massive. I think that's probably sufficient.
It's massive, right? But what's interesting is it's way less than a Googleplex. It's like ridiculously big. Okay, so what's a Googleplex, right? So a Google is a one with 100 zeros, and a Googleplex is a one with a Google zeros. So of course, 10 to the 69 is less than a Google. And so I think this it's something around, I might be 10 to 68, but so 10 to 69 is less than a Google. And so, so one with 69 zeros, and I'm talking about one with that many zeros. So it's way less than a Googleplex. It's a much smaller number. And that's the key point. That's the point, that it's much, even though it's massive, it's way smaller than a Googleplex.
And when most people speak of the universe, I think they're implicitly talking about the observable universe. And I think it would behoove us to explain just what the observable universe is and how big it is.
Yeah, so yeah, you're absolutely right. So I'm not talking about observable universe when I talk about Googleplexian universe. So just to be clear on that, I'm talking about something much larger. So the observable universe is about 10 to the 26 meters across, if I remember rightly. So that's the one with 26 zeros meters. Big, but certainly nothing. There's no Googleplexes floating around in that number. That's very small compared to a Googleplex. And so what is that? So that is essentially, it's kind of as far as the eye could see, is the way I like to sort of describe it. So you think about, so the universe has lived for a finite time. It had a beginning about 13.8 billion years ago. It's been growing in that time. And there's a limit to the distance that light could have traveled in that period. And so there's a region beyond that 10 to 26 meters where the stuff is literally so far away from us. We're not in causal contact with it in any way. So in other words, there's no way we could have ever exchanged a signal. Right, it's too far away. It's we can't see that stuff. To have communicated with that stuff beyond that distance, the light would have had to travel faster than the speed of light, and that's the limit. So that's kind of the sense. So there's this boundary, there's this shroud around us, around 10 to 26 meters, beyond which everything beyond it is too far away from us for us to have any, for light to have traveled to, for light from it to have reached us since the universe began.
Right. And my understanding is that physicists have no doubt that there is stuff beyond the observable universe. But does cosmology currently give any indication of how much stuff there might be or how big the universe could be? Or is this something that we're totally in the dark about?
No, it does. It does actually. So one of the things you can think about when you think about you can think about the shape of the universe. Now, so typically we assume that the universe looks the same everywhere and in all directions. It's called homogeneity, and isotropy is the buzzword that we use to describe that. But what that tells us actually, if you make that assumption, it's a good assumption on very large scales. That basically it looks the same everywhere. That means the shape of the universe there's not many possibilities for its shape. And one of the things you can imagine is that its shape is it's like a giant sphere in some sense. It's a three-dimensional surface of a sphere, but it's like a giant sphere. So you could imagine it's finite, and you could go all the way around and come back to where you started with, right? So it's huge sphere, okay? Or it's like a plane, or it's even like a saddle. These are the three possibilities. Now, the question is the object is that shape infinite, or is it finite? Well, if it's a sphere, it's certainly finite, okay? Spheres are finite. So if the universe is a giant sphere and you could sort of go across the universe and travel for billions and billions of years and come all the way back to where you started from, literally, like navigating the surface of the Earth, but doing it on a cosmic scale. So you can ask the question, do we measure that shape of the universe? And we do. We measure it with the cosmic microwave background radiation, which is this sort of radiation that's left over from the Big Bang. And we can look because the photons that make up that radiation, they travel through the universe and they feel its shape as they move through it, and we can detect that in the spectrum of the radiation. So that's what we do. We're able to put bounds on the on the shape of the universe, and what we know is that it could be a sphere, it could be a giant sphere, but if it is a giant sphere, it's a really, 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 really big one. So big that it looks flat to us. So we can't even tell the difference between it, whether it's we're in a sphere or actually we're just in a plane, because its sphere is so big. Well, how big must it be? Well, it must be, I think the number is in my book, but I remember, I think it's about 250 times bigger than the observable universe. It's got to be really big. So we know it's not. So that's kind of like, we know the universe is maybe of order 100 times bigger than the observable size. How much bigger it is than that, we don't know. We don't have an upper limit. It could in fact be infinite. We don't know.
And then before we calculate or talk about the distance, I have one. You said that when I gave my sort of naive formulation of the problem, you said that you didn't agree with my suggestion that mass was important. And I just wanted to clarify that, because if we're looking for my doppelganger out there, if there's far more mass in a region, then it seems much more likely that we would find a doppelganger of me there, because trivially, if there's no mass, there's no chance. So the density of the mass in the non-observable universe would be a very important number, as far as I can tell, if we're trying to figure out if my doppelganger's out there. Because if it's empty, then there just wouldn't be a doppelganger at all.
I mean, obviously, you're saying that because you yourself carry mass, and therefore doppelganger must carry mass. So you can't have a situation where you have vanishingly small densities. Clearly, that's true, but I think it emphasizes the wrong point. I think the point is really how many possibilities there are, and then you can ask so you take your cubic meter of space and you ask how many different ways different quantum states can describe that cubic meter of space. It's a large number. I think it's 10 to the 10. I think it's 10 to the 70. And then you can say, well, there's 10 to 70 possibilities. How far, so you're going to then start to move across space and start sampling these possibilities. And eventually you will see repetitions, maybe not repetitions of you, but repetitions of more likely things. But then eventually even the unlikely things start to be repeated. So you can actually do a calculation of, well, how unlikely do you have to be for there to be only one of you in a universe that's a googolplex meters across, and the number is tiny. You'd have to be ridiculously tiny, smaller than any other number. It's just really, really small number. It makes it implausibly. I mean, it could be that you're that unlikely, and we're all very special, but it's hard to justify it, I think.
Okay, and then it seems like a googolplex this is a number within which, given the parameters we've discussed, it's very, very you're going to find doppelgangers. But is there a more specific number where you think this is probably about the distance it would be that you'd find one doppelganger?
So this is where you relate it to the number of different combinations. Let's now the moment to start thinking a bit more about the calculation. So the calculation uses black holes. Okay. So it turns out that the black holes are the best storers of entropy in the universe. They're the best hiders of information, and it's kind of really, you can think of this quite intuitively actually. So when we talk about a black hole, there's only certain things that we can measure about it. We measure its mass, its charge, and its spin. It's famous saying that black holes have no hair. There's no bumps and bruises on a black hole. We just measure their mass, their charge, and their spin. So you can ask a question, right? Suppose you wake up one morning and there's a black hole in your garden. You're like, oh, this black hole just appeared in my garden. And you measure its mass, its charge, and its spin. Don't get too close because it's probably not a very big black hole, and small black holes are the dangerous ones. But anyway, so then the next day, you notice that black hole has changed by the mass of an elephant. So it's grown a little bit and it's changed its mass by the mass of an elephant. But you actually say, well, what's happened to that black hole? Has it swallowed an elephant? And you don't know. Maybe it's not giving up that information. It could have swallowed an elephant, but it could have swallowed a car that's got the same mass, and you can't tell because it's not giving up that information. It's hiding that information. That's now becoming entropy in some sense. So black holes carry they're the best hiders of information in the universe, and they do carry entropy. They carry a lot of entropy for their size. And so one of the things you can do is you can do an experiment. You can think about, like a thought experiment. You can think about, if you start off with take a cubic meter of space. What's the most entropy you can cram into that cubic meter of space? Well, it's the black hole that fills the space. Because black holes are the best. They're better than me and you at storing entropy. They're deeply gravitational objects. And so how much entropy can a black hole store? It literally is the best hide of information. And its entropy it goes like the surface area. It goes like the area, its surface area in units of the Planck length, which is a really tiny distance scale. So it turns out that for a cubic meter of space, you're going to get about 10. The entropy is going to be about 10 to the 70 of the corresponding black hole. Okay, so 1 with 70 zeros, that's its entropy. And the entropy is in turn the log of the number of possible microstates. So you can just exponentiate it and you get the number of microstates down. And so this then leads to the idea that we have this sort of kind of holographic image of the universe in some sense, that the degrees of freedom that you can use to describe, the ingredients you use to describe a cubic meter of space, you can think of as being kind of sort of stored on the edge of that space. And the number of degrees of freedom that you need, the number of ingredients you need is going to be e to the 10 to the 70, which I think is about 10 to the 10 to the 68 or 69 or something. And so that's counting the number of microstates that you have, right, that can describe a cubic meter of space. And it's no more. If you wanted it to be more, there's two things you could do. You could reduce what's called the Planck length, the length at which space-time breaks down and becomes quantum. You could reduce that, then the number would go up. Or you could sort of not have quantum mechanics, right? If you didn't have quantum mechanics, then you wouldn't be breaking this up. What quantum mechanics does is it discretizes everything. It turns them into quanta, right? You wouldn't have that. You'd have like continuums. And so the minute you go from discretum to continuum, then suddenly, finite quantities become infinite. And again, you'd have infinite number of possibilities. But we do have quantum mechanics and we do have gravity. We do have a finite Planck length. And so all these things together tell us that cubic meter of space only has a finite number of possible quantum states that can describe it. Now, of course, I'm making the assumption here that the physics doesn't change as I move across the universe. So in some sense, there's some sort of locality argument here, right? That there's a consistency in the physical laws as I move vast distances in the universe. And you could argue about whether that's justified or not. But if I assume it, then indeed, then as I move through the steps and move across the universe, then eventually you'll start to see repetitions of those 10 to the 68 or 69 possible states. So that's kind of the number, I think. Now, I think if I said I had a universe which was 10 to the 68, 69 meters across, it would be a stretch to say that you had a doppelganger. That's a rough ballpark estimate for the distance to your doppelganger, but it's probably, I now need to start to factor in that you're quite an unlikely thing, right? You're quite an unlikely cubic meter of space. So you have to so you really have to sort of absolutely swamp that number to start making grand claims about the existence of doppelgangers. But yeah, that's kind of the key number. I think I call it a doppelgangian, but it's probably a stretch to say that that's the distance to the doppelganger. Well, again, that depends on how you define a doppelganger. If you start averaging over internal degrees of freedom and you start not worrying about arrangements of electrons and so on and so forth, then the number will come down because you're not requiring such an exact match, of course. So there's swings and roundabouts here. You can make if you don't require such a precise equality to be a doppelganger, then you don't have to traverse such large distances.
Well, the last question I will ask about this is, do you really think that your doppelganger is out there somewhere? Is that something that you'd like gun to your head you would just say? You'd be willing to put your money there?
That's a good question. I don't know. That's not a satisfactory answer, is it?
No. It's okay. I mean,
if it is, it doesn't matter because I'm never going to meet it because it's so far away. It's in a realm of the universe which is just never going to have anything to do with me, right? So it's not a thing, right? So it's just, it may be out there. It may be talking to another Robinson somewhere, maybe. I'm never going to interact with it. I'm never going to be able to do a physical experiment that involves it. It's kind of removed. Do I believe it's there? I think it's plausible that the universe could be so large. So when you start to think about that, then maybe. I think I talk a little bit in the book about eternal inflation and trying to understand the initial conditions of the universe, why the universe started out as it did, and the idea of this sort of field jumping about in the early universe and causing the universe to grow, pockets of the universe to grow very, very quickly. And it continues to do this eternally and forever in all different pockets of the universe. Now, such a universe would be huge, truly gargantuan. So it's in that scenario, you can imagine that, well, maybe. So yeah, I don't want to say, I don't know is such an unsatisfactory answer, but the sort of the physicist in me just doesn't want to say yes, it's one or the other. So I'm going to say on the fence.
Yes, yeah, no problem. Well, thank you for doing this deep dive with me on the doppelgangers. I mean, there are so many fascinating numbers in the book. You go into special relativity, the Higgs boson, infinity, zero, vacuum energy. There are so many things, but I had planned to talk about all of them, but I think it was worthwhile just going into one in a lot more detail. But while we are on this subject, maybe we should finish out the rest of our time by sticking with black holes, holography, these sorts of questions. And I've heard of Graham's number before. It's a very, very large number, but I hadn't really considered it in connection to physics. And as you mentioned at the beginning of our conversation, that's a great way of bringing numbers like this to life. So what is Graham's number, and how does its decimal expansion connect to black holes and entropy, what we were just discussing?
So Graham's number, it was introduced several decades ago now by the mathematician Ron Graham. And he was, and for a long time, it was regarded as the largest number to ever to have been used in a mathematical proof. So he was trying to study a problem in a branch of physics known as Ramsey theory. It was, I'm not a hardcore mathematician. I don't want to go into too much detail, but essentially, it was a problem involving arrangements of sort of hypercubes in higher dimensions, and he wanted to get sort of he was looking for some particular property, and he wanted to get a bound on the dimensionality you needed to guarantee that this property occurred. And I think his lower bound was 6 or 13, but some ordinary number. And his upper bound, well, you think, well, maybe it's 100, maybe the dimensionality goes up to 100 or 1,000. No, his upper bound was this ridiculously gigantic number, which we call Graham's. Well, actually, it's not quite Graham's number. There's a bit of a sort of quirk of history there, but something like this number that we call Graham's number. And it's crazy big. This is a terrible estimate in some respects, right? That he's doing this problem and he's getting it. Oh, it's between these two numbers, 6 and that massive thing over there. And it's far beyond any of the numbers you normally think about. Certainly any numbers that you set billions, trillions, quadrillions. Forget them; they're nothing. A Google, nothing. A Googleplex is nothing compared to Graham's number. When you express it, you don't express it in ordinary language. You use a special notation, cross arrow notation, to describe it. It's just gargantuan. And so I was asked by Brady Harron to do a YouTube video about it, and I just wasn't satisfied with the idea of, I'm just going to describe the maths of it. I wanted to think about squeezing it into our universe. And so I started to think about, well, what would happen if I started to think about this? And I don't mean in the Knuth sense of this fancy arrow notation, but in the conventional sense that we normally think about numbers as some sort of decimal representation. And then I thought, well, actually, if I tried to do that, there'd only be one possibility, and that's that my head would collapse to form a black hole. It's just long before I even reach the number. So the idea is that you would imagine this number in your head, and its decimal expansion is sort of appearing in your mind's eye. And if you want to try each number carries a little bit of information. And the point is that information weighs. It really does weigh. I mean, if you take a photo on your mobile phone, then what happens is that photo will be stored. That information is stored on your phone, and actually the way it's done is it sort of raises some energy levels in the electron traps, and so that raising of the energy level actually makes the phone weigh a tiny bit more. Not much more, tiny microscopic amount, but it does weigh a tiny bit more. And actually, information does weigh. And so with each digit that comes into your head, very naively, you can think of it just as that's bringing in a little bit of weight, a little bit of energy into your head. And as you accumulate those, you're starting to cram too much into too small a space. And you know that eventually there's a limit to how much mass and energy you can squeeze into any given region of space before it collapses to form a black hole. Actually, in reality, as you started to try to do this, you started to try to shove this information in, of course, could your brain even conceive it? Do you have the neural capacity? Well, actually, in the book I talk about, well, maybe our brains are actually a lot better in principle at storing information than we realize. There's really some nice, funky ideas by a guy called Geert de Waal, who speculated about how brains store information compared to black holes. Really interesting ideas. We'll go into the details now, but they're really cool. Anyway, the point is that maybe we could store quite a lot, but of course, as you bring that information in, the brain's going to heat up, and you'd have to stop your brain from exploding, right? So you've got to try and keep it crammed in as the temperature rises. If you can somehow figure out how to store this information, so you've got to keep it crammed in, you've got to stop it from exploding. Let's suppose even if you manage to do all that, as somebody keeps feeding you these numbers of Graham's number, literally feeding them in, then even if you can survive, not manage to get your head to explode, then at some point, there's just going to be so much information that the only object the size of your head capable of storing that information is the best store of information of the universe, and that's a black hole. So your head has to become a black hole at that point. And actually, this will happen way before you even touch the sides of Graham's number, right? You just won't even get close. Truth is, if you want to carry on, you could get your friend to keep feeding you. You're an abomination now. Your head is now a black hole, and you could feed your black hole head more information, throw in more numbers. Don't know how they're really being stored, but anyway, you can imagine that. And then as that information goes into the black hole and mass is going in with it, the black hole is growing and growing and growing until it exceeds the size of the universe. Can it even do that? Possibly not, because there's this other limits that can cause the universe to break at that point. So it's a crazy scenario, but this number is so big that just imagining its decimal expansion well, you can never even get close to it. Your head would collapse into a black hole long before you got near it. It ends at a 7, by the way.
Great way of bringing the number to life, but there would be lots of doppelgangers in a Graham's number universe. I think it is fair to say.
Yes, I would.
Did you happen to calculate the size a black hole would have to be to contain Graham's number on its surface in Planck area units?
So I thought about this. It's basically the log of Graham's number. That would be the size of it, if I remember rightly. So that would be so the entropy. Let me see. So I think that was right. So that would be the length of the number. So I think you basically need a Graham's number sized head. I think is essentially it. The numbers are it's so large that that's the order of magnitude that you're talking about. It might be the log of that, if I remember rightly, but it's a huge order of magnitude, way bigger than and that would be in Planck. That would be in Planck units. That would be in units of the Planck length. So a gigantic head. Right.
So a black hole bigger than the observable universe?
It would have to be, yes. And so this is one of the things I talk about actually is that it's possible that there's a limit even within that framework that you. So our universe is surrounded by this horizon, this cosmic horizon. It might be what we call a de Sitter horizon, which is due to the fact that the universe has this positive energy of the vacuum, this positive energy of empty space. And as your event horizon of your black hole grows and it starts to approach this de Sitter horizon, if they two coincide, you reach what's called a Nari limit, and the universe breaks at that point. So you'd have to find a way to sort of reduce the vacuum energy of the universe as well to allow you to push that de Sitter horizon out much further. So there's a lot of it's a tricky business. It's in some ways, and this is one of the things I've mentioned, but Graham's number is too big for the universe. It's just too big for it. And this is one of the things, like, our numbers. So how have we conceived of this number, which in any meaningful sense, when you relate it to any of the meaningful scales that we talk about in physics, is too big for the universe? What the hell is that? It's amazing, really. And this is maybe where mathematics and physics overlap in places, but they also go apart.
Well, Graham's number is too big for the universe. The last thing that I'll ask today is about the largest number in your bestiary, and that is tree 3. And I don't know if you think it's too tough to explain without text or diagrams, but maybe we could give it a shot, and then I guess it also comes to life with the holographic principle, which we've been discussing. So maybe that would be a good last topic to end on.
Yeah, so tree 3 is even bigger than Graham's number. It dwarfs Graham's number, and the way this is something to do with what I call the game of trees. So it's the idea is you play this game of trees, and so we can talk about. So basically, the idea is you have seeds, a particular color, and branches. And so suppose you have seeds of one color. So the idea is to build trees. Where seeds are connected by branches, and you build this sort of forest of trees. Now, everybody has a go of drawing a tree, and there's certain rules as you in the game, which details we won't go into. But the idea is you build these trees, these trees that you can make up in this forest. And the rule is that the game ends if you draw a tree which contains a tree that came before. So there's kind of like living inside your tree that you've just drawn is one of the trees that you saw earlier. Then the game's over. And so the question is, can this game go on forever? Now, so this is the question. Now, one of the things you have to ask is how long can the game go on for? Well, that depends on how many different types of seed you've got. So if you've only got one color of seed, then the way the game works is the game can only last one go because you draw a seed, and then because there are limits to how many seeds you can put in any individual go, but the first go you would have to draw one, say a black seed, and the next one would have to be a black seed connected to another black seed by a branch. Now that contains the black seed. So it contains one of the previous trees. So the game's over. So this means that tree one, so the length of the game with one type of seed is 1. The game ends after that first go. You have 2 types of seed, right? So you've got like a black seed and a white seed. And you can try to do various things. You maybe put a black seed first, then you put a white seed. That's fine. That doesn't contain the previous one because it's a different color seed. And and then you can keep going. And then you could draw another one, and then the next going to end after that go. But that's actually a bad combination. What you're better off doing is you could draw, there are other combinations that you can try. And it turns out that this game will end after 3 goes. So tree 2 is 3. Okay? So still not a very long game. So this is a bit boring. No point playing this game with 2 types of seed. So you say, okay, well now I'm going to play this game with 3 types of seed. Right? And if you play this game with 3 types of seed, you might think, well, okay, if I had 1 type of seed, the game ended after 1 go. If I had 2 types of seed, the game ended after 3 goes. What's it going to after we've got 3 types of seed? It's probably going to be 15 goes or maybe 20. Nothing spectacular. Well, no, it goes off. It goes to this number which we call tree 3, which dwarfs Graham's number. So it's a crazy sequence. It goes 1, 3, tree 3, bang, right up there. It's an enormous number. So it's just bizarre. It's bizarre how big it is and how quickly it literally just goes off on one. It's absolutely bizarre. So that's the idea. So again, this comes back to one of the videos that I made, and I was trying to think about how do I talk about this number. It's just I can talk about what I've just said, but I want to go a bit further. So I wanted to imagine actually playing this game, and so. Imagine you play a game that's going to last for as long as possible. You're going to do the 3-seeded game. So in principle, it's going to go on for tree 3 moves, huge number. Well, you could ask, well, I'm going to play at the maximum speed possible. So each person is going to draw their seeds, their tree diagrams. Every plank time, as every 10 to the minus 43 seconds. You cannot draw it any faster because that would literally break space-time. Okay, so this is where space-time will be overwhelmed by quantum effects. So you can't draw it faster than that. So it's literally, realistically, you're not going to draw it that fast either, but let's put that as the limit. We're going to draw a diagram, we're going to draw a tree every 10 to the minus 43 seconds. And you're going to try and draw tree 3 of these. Well, what's going to happen? Well, you could be playing this game and, well, almost certainly climate change is going to overwhelm the Earth while you're playing, because it's going to take a long time, this game. It's going to last more than a year. It's going to last more than 2 years. It's going to last more than a century. Somehow you're going to have to try and stay alive, but let's suppose you manage that, or you're some sort of artificial intelligence that's playing this game. The sun is going to die long before you finish this game. Galaxies will collide before you finish this game. Literally, so you're going to have to move the game, clearly. Sun's going to swallow the Earth and all this sort of stuff. But let's suppose you manage all this. Right, so the game's going to go on and on and on. It's going to carry on beyond all the objects in the universe. We're going to enter an era of black hole domination, which will, occur in, I think it's 10 to the 40 years time, where literally all the stuff in the universe is just inside black holes, and those black holes will then slowly, evaporate. You're still playing this game, and it's going on and on and on and on until you eventually hit the heat death of the universe after more than a Google years. But you're still playing this game, and you're not even anywhere near the end. Actually, even more remarkably, there's something else. Before you finish this game, the universe will undergo what's called a Poincare recurrence, where it literally resets itself before you can even finish this game. Now, this Poincare recurrence is a really weird idea. It's basically the idea that if you've got any finite system, like a pack of cards, say, and so there's a finite arrangement of the cards. You've got a finite system, and or a gas of particles in a room, similarly, and you randomly jump between one arrangement and another. Okay, if you then eventually you will get back to where you started after a long but finite time. So that will happen with a pack of cards. You have a pack of cards, you've got one arrangement, you shuffle them, you get a different arrangement, you shuffle them again, you get a different arrangement. Let's say this is truly random. Keep shuffling, keep shuffling, keep shuffling, keep shuffling, keep shuffling. Eventually you'll get back to where you started. Same with the gas of particles. If the particles started out in the corner of the room and randomly move around the room, after a very, very long time, the system will get back to where it started, and all the particles will end up back in the corner of the room. It's called the Poincare recurrence. Now, our universe, being what we believe to be a finite system, which makes some assumptions about the nature of the expansion of the universe now and what's driving it, so-called dark energy and all those stuff. But one of the things we speculate that it could be true is that it is indeed a finite system, a large system, but a finite system. And because it's finite, it has it's described by a finite number of states. It has its Poincare recurrence. And so it will eventually reset itself, get back to where it started. And the time it takes to do that, whilst it's a huge time, it's truly gargantuan, it's nothing. You'd still be playing the game of trees. So the game of trees would still not be over. So you never get to finish it. So in some ways, it's like a physical obstacle to actually playing this game and actually finishing it, or taking it as far as it could go.
This is awesome. Well, Tree 3 is big, but it's just a drop in the pond of Tree Graham's number, which is just a quark in a drop in the pond of Aleph Nod, and then the continuum, and on and on and on. This has been so fun, Tony. It was so great. Thank you so much for having this conversation with me, and thanks so much for writing this book.
Pleasure.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.